Okay, so what we'll look at now is roughly what happens in reactions. I'm not going to, there's something that I call reaction mechanisms, and that is kind of like how does reactions happen and why it happens. I don't want to look at that. I just want to look at something a little bit more simple. We're going to look at moles and mass, okay? But in order to have its application, we're going to go just a little bit into reactions. So let's go back to what I was saying before. If I, for example, have an oxygen, I have a water molecule. Make it a little bit darker. I've got a water molecule, and a water molecule has oxygen and it has two hydrogens. Okay? Now water is H2O. I'm going to do something quick. Okay, so water we have as H2O, and then we have that H2O can, if we put a current, if we put electricity passing through water, it can produce hydrogen gas. Now remember, hydrogen can't be by itself, it needs that one extra electron. So we had hydrogen with his electron and another hydrogen with his electron, and now they are sharing that electron. And it can also produce oxygen gas. In the same way, oxygen can't be by itself, it has oxygen, and this time oxygen has 6 electrons, okay, but it needs 8. So another oxygen comes with his 6 electrons, like that, and now these two share an orbital and those two share an orbital. Okay, so now I've got 1, 2, 3, 4, 5, 6, 7, 8. Make sense? Okay, but again I need 2 oxygens. And what type of bonds are these? Covalent, ionic, or metallic? Covalent, excellent. So these are 2 covalent. So in other words, if I start with an oxygen like that, I can now produce the 2 hydrogens may form a covalent bond, okay, and the 2 oxygens, and oxygen also forms a covalent bond. But what do you notice? What's the problem in this reaction?
This is not balanced.
It's not balanced. Do you notice we need 2 oxygens in order to form an oxygen? So in other words, we're going to need another water molecule. So we draw in another water molecule. Okay, and now what will be produced? There was 2 hydrogens, so we need another 2 hydrogens, forms another hydrogen molecule and 1 oxygen molecule. So what I want you to see here is that in the end, if I balance this equation, for every 2 molecules of water, we will produce 2 molecules of hydrogen and 1 molecule of oxygen. Do you understand what the coefficient in a balance equation means? It tells me how many molecules will react with how many other molecules to produce how many of these molecules to produce how many of those molecules. You understand that? Okay. Another thing you should notice is how many protons in total do we have on this side? Oxygen has how many? Let's go back. 8 protons. And how many neutrons does he have? Also 8. So in other words, the protons and neutrons, 16, and then 1, 1. So in other words, we have a 16, a 1, 1, a 16, a 1, 1. So if I count the total number here, we have 16, 32, 4, 3, 4, 5, 6. So in total, we have an atomic mass of 1, 2, 18 plus 18 is 36. Now let's go and look afterwards. Well, could I have lost any of them? The protons and neutrons? No, they're still there. They're just now in other bonds. So how much should they be on this side?
36.
They should be 36. Let's see. 1, 2, 3, 4, and 16 and 16. 16, 16, 32 plus 4, 36. And this is what we call the principle of conservation of mass. The conservation of mass. That in a reaction, the total mass before must equal the total mass after. Makes sense, huh? Okay, now since we're now getting to that concept, obviously when we are working with well, let's quickly look at where does the mass actually come from, because we are saying 36 grams, and what that means is that 2 molecules of water is 36 grams. You can't even see 2 molecules of water. Okay, that's how few it is, and we're saying it's 36 grams. So if we talk about that 2, we're not really talking about molecules, but what we are talking about is a collection of molecules called a mole. Okay, so yes, it represents molecules, and yes, 2 moles is more than 1 mole in terms of double. So if there's moles is, how much is it again? 6,022 times 10 to the power of 23. Mole is a number. It is this many number of atoms or molecules. So in other words, if I say I've got 1 mole of water, that means I've got this many molecules of water. It will weigh 36 grams. So if I say I have 1 mole of hydrogen, it means I have 6,022 times 10 to the power of 23, okay, molecules of H2, and they weigh 1 gram. Okay, it's not difficult. Okay, so okay, let's do this. Okay, here's a hydrogen. One hydrogen atom. Now we can't really get 1 hydrogen atom all by itself, but just now imagine we've got this one thing. Okay, how much does this 1 hydrogen atom weigh?
1.
Apparently 1. Not really. 1, because this 1 represents, that 1 there represents now in grams. Okay, so it doesn't really represent grams. It represents the number of protons and neutrons, but now we are going to start looking at it in terms of grams. Okay, so from now on we're going to look at it in terms of grams. So basically what we are saying is how many hydrogen atoms must we have to have 1 gram of hydrogen. Okay, how many? So 1 hydrogen, like you can't even see hydrogen, that's how small it is. A gram is, well, let's take an example. A packet of chips is 36 grams. So divide a packet of chips into 36 small pieces. A packet of chips is about 30 grams. So divide it into 30 pieces. Will you be able to see the size of your chip if you divide it into 30 pieces of chips? A packet of chips? Not. It's going to be small, but can you see it?
Yes.
No. Okay. Now imagine that thing is like 1 billion times bigger than a hydrogen. Do you understand? A hydrogen molecule is, you can't see it with the eye. Okay. I can't remember what's the relative size of an atom, but it's like almost the size that you are compared to the sun. It's ridiculous. Like you can simply not see it. So 1 atom the weight of one atom, or the weight of a proton, for example, because that's in the end what adds weight is protons, is so small. It's not. It's like infinitesimal. I can't relate. Look, what is the weight of an atom? Weight of there we go. 9.1. Okay, so kilograms. So take a packet of potatoes. Let's say it was 10 kilograms. So take a packet of sack of potatoes. Okay. Now divide that sack of potatoes into 10. Okay. So it's about 1 kilogram, isn't it? If I divide it into 10. Now take that 1 kilogram and divide that into 10 again. Now you've got like a small little potato piece. Now take that small little and divide it into 10 again. Okay. Now do that for 31 times. How big is that size? So each time you're taking a tenth of 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 a tenth 31 times. Okay, it's ridiculously small. Okay, so so that's that would be the mass of a proton. Now if we that's the mass of an electron. Sorry, where's the mass of a proton? Why did they give me a mass of electron? Okay. Electron discover mass. Here's the mass. Okay, so the mass of a proton is 1.67 times 10 to the power of negative. Remember, negative exponent means divide. So it means take this number, a kilogram, and divide it with 10, 27 times. So now that you're taking like 1.5 kilograms, dividing it in 10, take that piece that you have. Divide that into 10 again, take that piece. So it's really small. Okay, but anyway, so 1 grams is definitely not a good representation. So if we talk about the atomic mass here, the atomic mass here, if I wanted to consider it as 1 gram, I will have to multiply the whole table. Do you understand? So I want to say, okay, I want to know how many protons and neutrons together will they be in 1 grams. So that if I say 1 gram, I'm actually talking about a certain number of protons and neutrons. Does that make sense? And the point is, it's that many. So this many protons will make up 1 grams of hydrogen. Is that okay?
Yes.
Okay, so from now on we will say that is 1 gram of hydrogen, but it actually represents 6,2 times 10 to the power of 23 molecules, or in this case atoms.
So for helium we say 4 times.
So in helium, okay, helium,
Yeah.
4 grams of helium will have this many helium atoms. Okay, so imagine, imagine we have a little container. In this container I can put, they've got little boxes. This container has little compartments. In each compartment I can put an atom or a molecule. Okay? This container can take this many molecules or atoms. So if I fill it up, I will have this many molecules or atoms in that box. So in every little compartment there's a molecule, and in total, now that's a massive container, by the way, or a very small container. That depends on how big the compartments are. Now if I fill everyone with a hydrogen atom, and imagine the container has no weight, has no mass, I mean, then after I filled every block, this thing will weigh 1 gram.
Okay.
If I fill every container, every block here with helium, in total it will weigh 4 grams.
Yes.
If I've got to fill everything here with chlorine, it will weigh 35.5 grams.
Okay.
Okay, so why does it weigh more? Because now when I put in chlorine in here, each chlorine molecule has 35.5 protons and neutrons. Okay. Candela, it looks like I'm confusing you more than I'm...
No, do you know? But did you get my question, sir?
Huh?
Because 1 mole of hydrogen, and hydrogen only has 1 gram. So 1 gram of that is 6022, times that.
Yeah.
So for helium, is it 4 times that number?
No, because you are not... what we're saying is this represents a quantity. So, in other words, if I say I have 1 grams...
So every gram has...
No, every 1 gram of hydrogen has this many molecules.
Okay.
Every 4 grams of helium has this many molecules. Okay, so in other words, this many molecules of hydrogen weighs 1 gram. This many molecules of helium weighs 4 grams. This many molecules, okay, of Peters. Okay, it's a quantity. I would count this many quantity, and then the periodic table will tell me how much that many molecules will weigh. Okay, now if and I think the boxes may be a good example, because I will call this box now a mole. It is a quantity, it's a number of certain, just like what can we think of that is a quantity? A million. Million is a quantity. So it's like saying 1,000,000 hydrogens weigh 1 gram. 1,000,000 heliums weighs 4 grams.
Okay.
So it's like a word representing a number. Does that make sense? So in that sense, mole represents a number, this specific number, and this number is called Avogadro's constant. Avogadro's constant. Okay?
Yes.
Is that okay? So, in other words, if I'm talking about a mole, I'm talking about a whole lot of molecules, or atoms, depending on what I'm talking about. Okay? If I'm talking about helium, it will be atoms. If I'm talking about hydrogen, it would be a molecule, because hydrogen is 2 hydrogen molecules, atoms. Okay, so that's the one part. Okay, so if I wanted to go and so in other words, if 1 mole equals, and now we're going to so 1 mole is equal to the atomic mass. Is that okay? 1 mole is equal, so if I have 1 mole of hydrogen, I have this many grams of hydrogen. If I have 1 mole of calcium, I've got the atomic mass of calcium in mass. Okay? So, if I have 2 mole, I have twice the atomic mass. Okay? So in other words, I have 2 of these boxes. So I'm doubling the boxes, which means I'm doubling the mass.
The boxes of 6,
yes, yeah. Because a mole now represents a box of this many. So if I have 2 of those boxes, I've got that many. Does that make sense? Okay, now the atomic mass is now represented by M. Okay, the mass that I have, 2m, this mass is represented by lowercase m. That's the mass that I have. Atomic mass is a constant for every, do you understand? So atomic mass is a constant, like for hydrogen it's 1, for helium it's 4, for chlorine it's 35.5. It's a constant, but it depends on how much of that I have. If I have 2 moles of that, then it's 2m, but the answer that I get is going to be represented by lowercase. That's my mass, literally my mass. So my mass is equal to the number of moles that I have. Here, this is moles. So I have 2 moles, which means I have 2 atomic masses, which is equal to the mass. So the mass that I have is the number of moles that I have times so this is my mass per mole. Capital M. The atomic mass is how much does it, what's the mass for every mole. So in other words, if I want to know what is the mass of a certain thing that I have, I can see, well, how much moles do I have, and then I multiply it with the atomic mass, and that will tell me the mass that I have. Does that make sense?
Yes.
Okay, now how do I know how much moles do I have? I actually have to go and count the particles, and for every 6,022 times 10 to the power 23, I'll know. So in other words, I seldom know how many moles I have. It's much easier to know how much mass I have. I just take a balance, not a balance, a scale. Okay, so just change this formula a little bit, divide both sides with a capital M, and then I get that the number of moles that I have is equal to the mass that I have divided by the molecular mass. So I'm trying to show you where this formula comes from. Now, why is that important? Because if we go back to what we said here, okay, every 1 molecule of water, no, 2 molecules of water produced 2 molecules of hydrogen and 1 molecule of oxygen. So imagine now I have, remember that container I was talking about, the mole. We'll call it the mole container now. Okay? Imagine in every slot I have a molecule, a water molecule. Okay? Now, according to this, I'm going to need 2 of them. Agree?
Yes.
And if I have 2 of them, and on this side, I will have a box, and in this box, same size box, 6 times 10 to the power 23, and another box. Okay, in this one I'll put my hydrogens. In this one I'll put my oxygens. Okay, so I take my first molecule and I break it up. I fill this one, but I can't fill this one yet because I need 2 oxygens. So I must take another one from this box. I fill another block here, and I'm able to fill 1 block here. Now notice that by the time I get halfway through, this box will be full because each time I'm filling 2 blocks. So in other words, I'll have 2 of these. By the time I'm finished with these, because every block here will fill a block, will fill a block here. But I need 2 of these to fill 1 block here. So by the time this one is full, I will have 2 of these ones. I'm just trying to show you this represents moles. How many moles I need. Okay, so in this reaction, okay, if I now have 18 grams of water, as an example, I might now ask, well, if I had 18 grams of water and I can completely dissociate it, it's not dissociate, well, let's put now just say into hydrogen and oxygen, how much, well, the question is now how much hydrogen, how many grams of hydrogen will I have, and how many grams of oxygen will I have? Okay, so I'll look at my reaction formula. I'll balance it. We balance it. Okay, and then I'll notice, okay, if I take the number of moles of water divided by the number of moles of hydrogen, okay, I'll get 2 divided by 2, so I'm looking at the coefficients, okay, and I'll get, the answer is 1. Okay, now my question is, this is the standard, this is what would normally happen. Now I'm saying, okay, but I have 18 grams of water. So, if I have 18 grams of water, how many moles of water do I have? So I have this is fixed. I know now that this NH2O divided by NH2 is equal to 1. Now I want to know, well, how many moles of water do I actually have? Okay, moles is mass of water, so let's put this mass of H2O divided by the molecular mass of H2O divided by the mass of H2 and the mass of the molecular mass of H2. This must give me 1. Have I lost any of you at any time now?
No.
No, you're still with me. So can you see all I did was to replace N with the formula mass over mass, is it?
Yes.
Okay, so now I see, okay, the mass here of H2O is 18. The molecular mass of water, let's quickly look at that. Water is 1 oxygen, so 16, and 2 hydrogens. So 1, 2, so that's 18. So that's great. That's 18 over 18 for the top. Now I want to know what would be the mass, how much mass of hydrogen would be produced. So this is still unknown. I don't know what the mass of hydrogen produced is, but I know what the molecular mass for hydrogen is. What is the molecular mass for hydrogen? 2, because I've got 2 hydrogens to form 1 molecule. Well done. So this would be 2, and my final answer must be 1. When I divide it, I must keep that ratio, because every 2 moles of this one produce 2 moles of that one. So for every box I produce 1 box. Okay, so I now just continue to multiply. So at the top I get a 1, but I multiply both sides with this denominator. So I get on the other side mass H2 over 2, and then I multiply both sides with a 2, and I get that the mass of H2 is equal to 2. Okay, so if I had 18 grams of water, I would produce 2 grams of hydrogen. How many grams of oxygen will we produce?
16.
It must be 16, because we started with 18 grams. And it must be 18. So the next one is very easy to get. But let's say we didn't do it that way. Okay? We could have done it that way. We could have done the same thing. We could have said, well, if I look at the moles of water compared to the moles of oxygen must be, for every 2 waters, we produce 1 oxygen. With me? So now we just do the same thing. So the mass of water divided by the molecular mass of water divided by the mass of oxygen, and the molecular mass of oxygen is equal to, the answer must equal 2. And so now I substitute, I get 18 over 18 over here I get mass of oxygen is what I'm trying to find, and the mass of the molecular mass of oxygen is 16. Okay, and this must equal an answer of 2. So now I get, when I multiply here again, I get 1. I multiply both sides with the denominator, so I get 2 times the molecular mass of oxygen is not 16. It should be 32 because there's 2 oxygens. Okay, so let me just fix that. This should be 32 because there's 2 oxygens, isn't it? You with me? Let's see, okay, so it's 2. So this is 1 is equal to 2 times this will be, the 2 will cancel with the 32, so there will be mass oxygen over 16, and then just multiply both sides with 16, and so I get the mass of oxygen will be 16. So usually they teach it with a table, and I used to teach it with a table. Sorry, next. I used to teach it with that table where you have your ratios, and I just like this method, it's simpler for me. So I'm going to stick to this as I explain it. If you prefer the table method and you're good at filling in that table, very few people are. Yes. That table sucks. So I'm going to stick to this, and so let's just look at an exam type question with this in it. Okay, I'm going to look at this question, but I just want to show you, if you forget Avogadro's constant, it's usually in your paper. Is it there?
Yes, it is on top.
On top?
Yes.
Did I miss it?
Yes.
Did I not read it?
It's there. Go down, yep.
Oh, there we go. 6,02 times 10 to the power 23. Okay, I say that because I want to show you here. Okay, I say that because here, I copied the wrong thing. Here we go. Here you'll see they say study the following reaction equation. Here they give you that reaction equation. They give us how many grams of this reacts with how many grams of water. So there's our aluminium 2 sulfide. The first question is define mole. Okay, so mole, how would you define mole now? Remember I said a mole is a quantity. What is that quantity? A mole is like a million. A million is 1 times 10 to the power of 6. A mole is?
So you say you should write down the constant.
Yeah, that's what a mole is. A mole is 6,022 times 10 to the power of 23 molecules, or
so there's no word. Wow. Okay.
Molecules or atoms.
But so they say define, they didn't say give the number or the constant.
But that is what mole is. It's like define million. Okay. What is million? Million is. So it is the definition of mole. It's that many. Okay, now you could say it's an Avogadro constant of. Well, you could have just said that it's a quantity. Okay. Which reactant is the limiting reactant? So what do you guys think they mean by that? Which reactant is the limiting reactant? Show all calculations.
Aren't they trying to and isn't it about the using up or something?
Okay, so if they say which is the limiting reactant, what does that mean in terms of using up? Would that be the one that is used up first, or that remains afterwards?
No, I used up first.
Yeah, because it will limit. If it's used up, I can't go any further. Okay, so they ask which reactant is the limiting reactant. Show all calculations.
So what
Give
are
me
we
some
gonna
ideas.
calculate?
Yeah?
What
Sorry?
are we gonna calculate?
Yeah, what is the limiting? Like, what we calculate?
In other words,
Like
you
number
just
of
told me which reactant will be used up.
Are we calculating the number of moles?
No, don't
Yes.
think like that. Think about answering their question. Which reactant will be used up? Like, what will we look at?
The grams?
Green. Okay, notice here. Every 1 mole of this must react with 6 moles of that. So the question is, how many moles of aluminium sulfide do I have? How many moles of water do I have? Do I have 6 times as much water in terms of mole? You don't know. By looking at it, remember, mole is not grams. Mole, guys, moles is not grams.
Yes.
Mole is a quantity. 1 mole of water is 18 grams. 1 mole of aluminium sulfide is 150 grams. So, do we have 1 mole of aluminium sulfide? 1 mole of aluminium sulfide is 150 grams. How do I know? Well, aluminium is 36. I've got 2 of them, so I've got 72. Sulfide is, I can't remember, but I did the calculation before. It comes up to 150. I'll do the calculation for you as well, but I'm trying to get you to understand the difference between moles and grams. You can't look at that and say, no, water isn't 6 times as much as aluminium. You don't know how many moles of water you have. You don't know how many moles of aluminium. We work in moles. We don't work in grams. But we're given grams. Do you understand? When we did the reaction, we needed 1 mole box, 2 mole boxes, and it produced 2 mole boxes of hydrogen and 1 box of oxygen. We didn't even look at the mass. But we can only measure mass. We can't measure moles. So we measure mass, convert into moles, and then make a conclusion again in terms of mass. Does that make sense? Because we can work with mass, but we need, our equation represents moles. Okay, so do you understand? So this is how we'll do it. We'll say, okay, what we need is my ratio of aluminium to sulfide, okay, divided by my aluminium, my water must be, for every 1 mole of this, I must have 6 moles of that. Okay, now I can't substitute, well, I can substitute both. Okay, so let's see if that's what I have here. Okay, so on this side I have N. This one becomes the mass of aluminium to sulfide divided by my capital mass of aluminium to sulfide, okay, divided by mass of water and the capital mass of water. Okay, you with me? You understand so far what I've done? Okay, now you've got one of 2 choices. Now you can replace both of these, isn't it? Because you've got the value for both.
Yeah.
But one of them is going to be used up, the other one not. So only use, do you understand what I mean? One of them is limiting, one of them is in excess. So I'm either going to have excess aluminium sulfide or excess water. So only use one of them and see what result you get and make a conclusion. So which one do you guys want to use? One, both, aluminium sulfide, water, or both. It doesn't matter.
Can we use both?
Let's use both. Let's use both. But that's the problem, guys. You can't. Don't just substitute. Don't just use formulas and substitute and solve. I know that's how I teach the course often. But think. Okay, you'll have to think that that this represents the moles used. 1 mole used needs 6 moles used. So I either must use I must either use all of my aluminium sulfide and work out how much water I will need. And if let's say I work out and I need 16 grams of water, but I have 17, which one was in excess? Water. Do you understand? So, or I must say, okay, let me use up all of my water and see, well, if I use up all of my water, I need 30 grams of aluminium sulfide. Which one is in excess?
The aluminium. The water.
The water, because I don't have 30 grams of aluminium sulfide. Do you understand what I'm saying? Is been thinking, okay, but let's say you did use both. Let's see what you have gotten. You would have gotten that the mass of aluminium sulfide that I have is 28, divided by the mass of aluminium sulfide. I'm not going to waste time on that. If you do it, it's 150. Is that okay?
Yes.
You trust me? Okay, don't. Go and calculate it at home. The mass of water that I have is 17. The mass of water per mole is 18. And then quickly get that. Just check with me, please. So 28 divided by 150 times 18 divided by 17.
Yeah, correct.
So 0,197, about 0,197. Now how is that helpful?
It doesn't show.
Yeah.
It does actually.
But then, okay.
The thing is, we need to compare it to what we need. We need this ratio. So between these two values, which one is bigger?
The 6 is big.
What do you mean, sir?
Which one is bigger? 1 divided by 6 or 0,197? Which?
0,197. Isn't it?
I don't know, test it.
Okay,
1 divided by 6.
Is
That's what
1 divided by 6 is 1.6666. In other words, this is smaller than 1,97. Now look at your easy 0,197, sorry. Look now at your easier. This is 0,168. Didn't mean 197, 111. Okay, now look at what you now apparently think is easier. Okay, it's not difficult, but notice that this one can also be written as a fraction, isn't it? I can somehow write it as a fraction. Okay, if I write it in a fraction, let's try get our denominator to be 6. It doesn't matter what the numerator is, but let's make the denominator 6. Which side will be bigger? So okay, so let's say this is, it doesn't matter. If I want my denominator to be 6, I'm saying that I'm using 6 moles of water. I need 1 mole of aluminium sulfide. If I make my denominator the same on both sides, which numerator is the bigger numerator? It doesn't matter what this top is. Okay? If I make the denominator the same on both sides, will the numerator be bigger or smaller than 1? Why?
You also have to times it by 6.
Yeah. So what exactly that.
Yeah.
So let's do that. That's beautiful actually. That's a good way of looking at it. So let's make the denominator 6. So let's divide it by 6 and times it by 6. What do you get?
Yeah.
What do you get?
It's not going to give
Same.
me 0.197.
No, what do you get here?
Same.
No.
0.197. Because you divide.
No, you must
by
multiply
nine.
this, guys. You must multiply.
By 6.
You
And then divide by 6.
no. You still have your divide by 6. We want to know what's at the top.
Oh.
Oh.
Of course, you get the same.
It's 1.182.
1.82.
182.
So listen now what you've calculated. You've calculated the ratio. And you are saying if I have 6 with the ratio that I have, whatever that ratio is, if I had 6 waters, I would have this many aluminium sulfides. Which one is in excess? I only need one, but I have more than enough aluminium. So I've used the ratio that I have. So if so the ratio that I have, if I took that ratio and made my water 6. So it doesn't matter how much water I have now in moles. If I made it 6, I must multiply both with 6. That's what you did. It was actually beautiful. I multiplied the denominator with 6 and the numerator with 6. So I've made my water 6, and then I see, well, then I would have an excess of aluminium sulfide.
So water. The 6 was the limiting, isn't it?
Well, it now depends. If this was, your question is which one is in excess, and then you see, oh well, this one is in excess.
Yes.
So because my aluminium sulfide is in excess, it makes water the limiting factor.
Okay, yeah.
If you got an answer less than 1, then you know, well, water was then in excess. Because I needed 1. So if I want to have 1 in the top, I must multiply, no, I don't even know what you will do to get it. I like the divide. So point being, if my numerator was less than 0, or less than 1, I would know, well, I don't have enough aluminium sulfide to use 6 waters. So my aluminium sulfide will be my limiting factor. Does that make sense?
Yes.
You see how you're going to have to interpret this. It's not basically substitute into a formula and get your calculator tells you aluminium sulfide in excess. Okay, it doesn't do that. You must interpret. Okay, but nevertheless, if you have a question like this in the future, probably it's easier just to use one of the two and see what answer do you get.
Yes.
Does that make sense? So either use water or aluminium sulfide, then you'll actually have an answer and you'll get, okay, the aluminium sulfide that I need is equal to an answer, and let's say that answer is 25 grams. And you see, oh, I've got 28, which means I've used up all my water and I still have aluminium sulfide. Water is limiting reagent. You understand?
Yes.
Okay, let's go to the next question. There's a few difficult questions here. Calculate the mass of H2S that is supposed to form. Now, which gram is appropriate to use? Which is a valid gram? There's 2 grams here. Which one should I be using?
I'm thinking the water.
The water, because he's the one we're using up. So we're going to use 17 grams of water. Now we want to work out how many grams of aluminium sulfide will be formed. So let's go.
Isn't it how many? Sorry.
Calculate the mass of, hydrogen sulfide. Dihydrogen sulfide. Is this a covalent, ionic or covalent bond? Covalent, good. Okay. So the reason why that was important is because I need to know what reactant mole am I going to use, and I'm going to use water reactant mole divided by what I'm trying to calculate. Probably you can turn it around as well. Let's make what I'm trying to calculate the top. Just easier to work with a numerator, solve a numerator than solving a denominator. So let's do that. Doesn't matter. The number of moles formed of H2S divided by the number of water used is equal to, now we go up, 3 formed, 6 used. Okay, so 3 moles is formed for every 6 moles used. Now we substitute the mass of H2S divided by the capital mass of H2S divided by the moles of water. The mass of water used is 17, the mass of water is 18, is equal to 1 over 2. I'm just simplifying that, 3 over 6. So I multiply both sides. This one I can go see, it is hydrogen sulfide. Where's my periodic table? Come here. Okay, hydrogen is 2 hydrogens and sulfur is 32, so this is 34. Agreed? Okay, so I get the mass of hydrogen 2 sulfide that I'm trying to calculate divided by 34 is equal to 1 over 2 times 17 over 18. Still good?
Yes.
Okay, so the mass of hydrogen 2 sulfide that will be produced is a half times this, so 17 over 18 times point.
Did you say 17, sir?
Oh, I did not. Okay, so 17 over 18 times 1 over 2 times 34 is equal to 16.06.
And so can I ask, was it important to check if the equation is balanced? Or?
Yeah, of course, because that's where we got the moles from. Yeah. Sorry, I didn't check that, but that's definitely, if it's not balanced, then I'm using the wrong coefficients.
Yeah. So they didn't state that it's balanced. So you didn't know that it's balanced.
No, you shouldn't. If they didn't state, you should check. I should have checked. I'm sorry. But luckily, I know this. Luckily, they did balance. Can you imagine balancing this one? It looks difficult. When you have big values like that, 6. I'm not allowed to say that.
Yes, I mean, imagine if it's difficult for you.
Why did you say it looks difficult? I didn't say it is difficult. A lot of things are difficult for me, but I make it easier by thinking.
Wow.
I promise you that's the difference. I promise you that's the difference. Okay. If the mass of the gas in question 1.3 occurs at standard conditions, calculate the volume of the gas. Okay. So I want to show you here. In our we are given a molar gas volume at standard temperatures. Okay. Now this tells me that this is the volume that 1 mole of gas will occupy. So remember, a mole is a quantity. So 6,02 times 10 to the power of 23, this many particles of gas will occupy this much space. Doesn't matter what gas it is. Okay? So 1 mole of gas takes this much space. If we wanted to calculate if the mass of gas occurs at standard temperature, calculate the volume of the gas. Give me some thinking. We know this, that the volume per mole, in other words, the molar volume, is 22.4. 22,4.
What's the formula for calculating volume?
No, don't go to formulas. We're telling you, every mole of gas takes this much space.
Aren't you gonna take that and then times it by the Avogadro, that guy's number? Because why not? Because you said that.
And I'm just saying it's a constant. In other words, the volume is the volume that at standard temperature that 1 mole occupies is a constant. The space that 1 mole occupies, the mass is different, but the space is constant.
Can't we do what we did the last time about the mass and the mole thing, and then try and break it into the volume?
You guys aren't thinking. Mechanic, please help me. Do you know? At least the girls are bold enough to answer. Come on.
The other way is the same. It's more tricky. It's just because it's what's more real than the one.
Guys, look at this. This is volume per mole is equal to 22,4. What do we need to find volume?
Mole.
Mole. So all I need to know is how many moles. If every mole occupies this much space, I want to know, well, how many moles do I have? If I have 2 moles, it must be 22,4 times 2. If I have 3 moles, I must multiply by 3. So, depending, I will take 22 times my mole. If every mole takes this much space, I need to know how many moles I have so I can multiply with it. Was there a formula? No, it was thinking. And it's not even a complex thinking. It's just understanding what does it mean. If I say I drive 30 kilometers per hour, how far did I drive? Well, how many hours did you drive? Do you see? Per hour, I need to know how many hours you drive to tell you how many kilometers you drive. So if you drive 2 hours, you drove, you see where I'm going with? Okay. So we need to calculate the moles. The moles of H2S is the mass divided by the molecular mass. The mass we calculated at 0.6, the molecular mass of this was 34.
34.
So what? How many moles is that, please? Okay. Mole, and that is what I'll multiply 22,4 with, and then what do I get?
10.58.
Sorry?
10.58.
Okay. So can you see I almost have half a mole, which is why I almost occupy half of this is 11.2. So you see it's almost half of that. So it makes so much common sense, but we just want formulas. Okay.
This is physics.
Yes.
Please.
There's no common sense.
Please.
I've not shown you one thing that you had to go study. I've not shown you one thing that doesn't make sense. This makes all sense. So what? I can only accuse the mind that's reading the question. I cannot accuse the question. If only this much H2S is formed, calculate the percentage of impurity of Al2. Okay, so what they're saying is that, and this I grant, this is a difficult question. I grant that. It is unusual question. But if we talk about an impurity, it means among the products, there's still some reactants.
Yes,
Which we don't need. So in other words, the products are being contaminated with some reactants. There's still some reactants there. Okay? Now, what is the, if we want to use the percentage impurity of this, we will take the mass of Al2S3 divided by the total mass times 100, isn't it?
Yes.
Does that make sense? So after the reaction has occurred, what is the mass that there is of aluminium sulfide? And because it's a percentage compared to what? Compared to the total mass. Does that make sense?
Yes.
You could have used mole and the total moles, okay? But it doesn't make sense because a mole of this is different than a mole of that. But a gram of this is the same as a gram of that. Okay, so that's why we use mass. Okay, so what is the total mass of this system before, after the reaction?
After the reaction.
Obviously, they didn't say it, but they should have said that it's a closed container because it's producing a gas. They should have said that.
I have to find it.
No, you don't.
You should have to plus maybe.
Yeah,
add
what-
together?
Which?
Add the grams for 28 and 17.
Exactly, that's a conservation of mass. The mass before and the mass after must be the same. You get that? So we know what the total mass is. It's 17 plus 28. That's 30, 40, 45. So I know 45. So what I want to know is how many grams of aluminium sulfide is left.
Didn't you say 45? No.
No, so in other words, how much, remember we're saying impurity means, in other words, how much. Remember, water was the limiting agent, which means there was an excess of aluminium sulfide. And 14.28 grams was produced instead of what we calculated 16.09. So not even all of the aluminium sulfide and water reacted. So there's still some impurities. So how will you go about to work out how many aluminium sulfide is left?
I'm just gonna take what is expected, the 14.28 and subtract it from
28.
but 28 is that.
No, because if you subtract this from the 45, is that what you're saying?
No, not from the 45. From what we calculated.
It's easier than that. It's six marks, but you can do that, but you're taking a long route. Guys, all you're trying to know is how much aluminium sulfide is left. How do you work out how much aluminium sulfide is left?
Minus from the original.
Minus what from the original? You don't have to give me an answer, like a value, but what would you subtract from the original? How much was?
Used up.
Used. So we need to work out how much was used. How do we do that? Well, it's what this do. So we want to work out the mass used of aluminium 2 sulfide divided by the mass of aluminium 2 sulfide. In other words, this is the N. Divided by, and now what they give us, the mass of H2S divided by the capital mass of H2S. Okay, now this must keep the ratio in the equation. The ratio in the equation was that every one of these produced 3 of these. So every one of this produces 3 of that. You with me?
Yes, sir.
And now we're just going to work out the unknown that's being used.
Okay.
Make sense? Okay, so mass of aluminium 2 sulfide divided by the mass of, I have this one 150 divided by, that one is 14.04, is that what they said? 28, sorry. 1428 divided by 34 must be equal to 1 over 3. So I just multiply that on both sides and I get the mass of aluminium 2 sulfide is equal to 1/3 times this 14,28 divided by 34 times the 150 as well. And what do we get?
0.14.
0,14.
Am I right?
I don't think so.
21.
Yeah, it's a nice number. 21.
Yes.
Yeah, okay. So what did we just calculate?
The one that was used.
We calculated the quantity used. Is that what I'm going to substitute up here? 21? Why not?
Aren't you gonna say 21 minus 14.28?
No, because 14.28 is hydrogen sulfide. I want to know what's the percentage of this. 28. So there was 7 grams. That's left.
Oh, yes.
Which is, in terms of percentage,
15.56.
Yeah.
okay.
Jeez. Yo.
Okay, this was the last question in the paper, and I don't. It was last year's June exam.
June.
And, no one got it.